Hi, I'm Mark Barsamian with the Ohio University Math Department. In the previous video, I introduced the concept of betweenness for real numbers and betweenness for points in a metric geometry, and I ended that video with a couple of basic examples involving betweenness of points. In the current video, I'll discuss more advanced properties of betweenness. This material is produced for Ohio University Math 3110, College Geometry. The reading for this video is just a few pages, pages 49 to 51 of section 3.2, Betweenness, in the book Geometry, a Metric Approach with Models by Millman and Parker. The homework is this collection of 6 exercises from section 3.2. In this video, I'll be discussing properties of betweenness, including things like this, that outside points can be reversed in the symbol for betweenness, be discussing the relationship between betweenness and coordinates. Remember, the definition of betweenness mentions distance. Be discussing some facts about 3 distinct collinear points in a metric geometry. Be discussing betweenness of points expressed using the vector representation of a line. Remember, that's something we can do in the Euclidean plane. I'll be discussing the existence of points with certain betweenness relationships, and finally we'll end by discussing betweenness for 4 points in a metric geometry. Let's start by recalling some important stuff from section 3.1. In that section we learned to use vectors to describe lines and rulers. We could describe Cartesian lines this way. Given 2 distinct points in the Cartesian plane, line AB is this set. We take that symbol A and we put it here and here. We take that symbol B and we put it here, and we put a parameter t there. So that's a quick way of building a description of line AB. That can be done in the Cartesian plane. Now remember, the Cartesian plane is the incidence geometry that's used in the Euclidean plane and in the taxicab plane and in the max plane as well. Also in section 3.1, we discussed how you can use vectors to describe rulers in the Euclidean plane. Here's how that works. If you have a Cartesian line, LAB, then this function from that line to the real numbers, defined this way, is a ruler for that line. Now remember that all of the points on line AB can be written this way. They all are something of that form. So our description of our ruler is going to have to show what happens when you feed that ruler a point on the line. Well, the description uses this description of points on the line and explains what will happen when you feed one of those things as input. So here's the description. If you feed one of those points into the function f as input, you feed them into that ruler, then what comes out is this real number. That's the output. Notice that real number is constructed by finding the number t, whatever that number t is, you put it there, finding the norm of b minus a, and then multiplying those two things together. That's the prescription for getting the output of that ruler. Now recall some important stuff from section 3.2 that was introduced in the previous video. Here there's a typo. We had the definition of betweenness for real numbers. So this symbol, x star y star z, you use when x, y, and z are real numbers. It's spoken. Y is between x and z. And what it means is either this inequality is true or this inequality is true. Now we also discussed the fact that betweenness for real numbers is related to the distance between them. That is, we had this lemma. Given distinct real numbers x, y, and z, the following 2 statements are equivalent. That is, they're either both true or they're both false. This statement, x star y star z, that is to say y is between x and z, and this statement, that those distances add up. Those are either both true or they're both false. We also discussed the definition of betweenness for points in a metric geometry. This symbol, a-b-c, spoken, b is between a and c, you use when A, B, and C are points in a metric geometry. And what it means is that these two things are both true. A, B, C are distinct collinear points, and the distances add up. That is, the distance from A to C equals the distance from A to B plus the distance from B to C. So in the current video, I'll be discussing properties of betweenness. The first property is this. The outside points can be reversed in the symbol for betweenness. So this theorem is really just a corollary of the definition. Given points A, B, C in a metric geometry, these two statements are equivalent. A-B-C and C-B-A. That is, B is between A and C is equivalent to B is between C and A. Now the proof is very simple. I'll let you read the book for that. But it's nice to have an illustration. An illustration of A-B-C could be this picture. An illustration of C-B-A could be the same picture. So it makes sense that those two things are equivalent. Another property that I want to discuss is this. Betweenness of points is related to betweenness of coordinates. So here's the statement. If you're given collinear points A, B, and C on a line L with a ruler F in a metric geometry, the claim is that these two things are equivalent. B is between A and C, and F of B is between F of A and F of C. That is to say, the betweenness of points is equivalent to the betweenness of their coordinates. Now there's a nice proof of this theorem in the book on pages 49 to 50, but as with most proofs in our book, there are no drawings. It's helpful to at least illustrate the statement of the theorem. So the theorem says that these two things are related, that is, they're equivalent. Well, let's just see if we can draw an illustration for each of those things. So let's illustrate A-B-C. That is, B is between A and C on line L. So there's an illustration of B is between A and C. Now how do we illustrate this? F of B is between F of A and F of C. Well, those are real numbers. They live on the number line. So let's draw the number line and draw those real numbers. Now we could add some more stuff to this drawing. Notice that you get from one drawing to the other by using the function f, that is, using the ruler. The ruler f takes as input a point on this line and spits out as output a number in the real numbers. What this theorem is saying is that these two pictures are equivalent in a sense. So we can convey that by doing something like this with our drawing. So there is a way of illustrating an equivalence theorem. You draw a picture corresponding to each of the statements that are being declared to be equivalent, and you just add something like this to convey that they're being shown to be equivalent. Let's go on. Another property I want to discuss is this corollary about three distinct collinear points in a metric geometry. It's a fact about three distinct collinear points. If you're given three distinct collinear points, then exactly one of the points is between the other two. And now how would the proof of this go? Well, it's very short. Suppose you're given three distinct collinear points in a metric geometry. Well, since they're collinear, there's a ruler for the line that they lie on. We can just say, let f be a ruler. Such a ruler exists because we are in a metric geometry. Remember that one of the defining characteristics of a metric geometry is that every line has a ruler. Now we can say that f of p, f of q, and f of r are distinct real numbers. We can say that because f is known to be injective, because f is a ruler. Remember that rulers are bijective functions. So if you feed in distinct inputs, then you get out distinct outputs. Remember that one definition of injective is if two inputs cause outputs to be equal, then the inputs must have been equal. But there's a contrapositive version that says if two inputs are not equal, then the resulting outputs will not be equal. So if you feed in points that are not equal to each other, then you get out numbers that are not equal to each other. So we use the fact that f is injective. Now, since we have three distinct real numbers, we can say for sure that one of those three numbers will be between the other two numbers. That's just by the property of the ordering of the real numbers. Now, because of the previous theorem, the corresponding point must be between the other 2 points. Now, we need to be more precise here. Let's go back and look at the previous theorem. The previous theorem says this: these are equivalent. The theorem doesn't say that either one of them is true. So if you're going to use an equivalence theorem, you really need to be more clear, because again, the equivalence theorem doesn't tell you that either one of these things is true. It just tells you that if one is true, then the other is true. Now, which is the thing that we knew was true? We knew in our situation, we knew about the betweenness of the coordinates of some points, and we used that to claim the betweenness of the points. So when I cite that theorem, I really need to say more. I need to say so again, instead of just saying by theorem 3.2.3, I really need to say precisely how I use the theorem. First of all, we use statement 4. We knew something about the betweenness of the coordinates. And then we used theorem 3.2.3 in this direction. We knew that 2 was true, and so the theorem allows us to say that 1 is true. So when you use an equivalence theorem like this one in a proof of some other fact, you always need to cite the theorem number, but also say how it's being used. Let's go on. This theorem 3.2.3 can be used to formulate criteria for determining when collinear points ABC have this betweenness relationship on certain particular kinds of lines. So for instance, here's the betweenness condition for points on a Poincare type 1 line. That is a vertical looking line. Consider 3 points that are on a Poincare type 1 line. We ask, when is this betweenness relationship going to be true? Well, by that theorem, the betweenness relationship for those points will be true exactly when this betweenness relationship will be true for the numbers f of A, f of C, f of B. That is those coordinates of those 3 points. But this betweenness relationship for those coordinates, for those numbers, that just means this. Either the coordinates satisfy that inequality, or the coordinates satisfy this inequality. Now, the standard ruler for a type 1 line is this function, the function from the line to the real numbers defined by this. F of x comma y is just ln of y. So that means that if I feed these points, A, B, and C, into that ruler, the coordinates that I get out are going to be, the coordinate of point A is, f of A is ln of ya. And the coordinate of B is this. F of B is ln of yb. And f of C is this, ln of yc. Now those are 3 numbers, and they have to have either this betweenness relationship or this betweenness relationship. So we're interested in the cases where this is true or this is true. Now this function, ln of y, is an increasing function. So these inequalities will be true exactly when this is true or this is true. So that means on a type 1 line in the Poincare plane, the points would look like this. So that's one configuration that would correspond to this inequality. YA is less than YC, which is less than YB. So again, this is a criterion for determining when points on a Poincare line have this betweenness relationship. If either of these inequalities is true for points on a type 1 line, then the points are going to have this betweenness relationship. Let's go on. Now, betweenness of points can be expressed using the vector description of a line. Now remember that the vector description of a line is available to us anytime we're talking about the Cartesian plane. When we're talking about Cartesian lines, we can describe lines this way. But we're going to be talking about betweenness. So betweenness is something we can only discuss in a metric geometry. Now we've discussed a few metric geometries, but only in the Euclidean plane have we used vectors to describe rulers. So we have this description of rulers in the Euclidean plane. We have this description of lines in the Euclidean plane. So proposition 3.2.5 says this: given 3 points in the Euclidean plane with A and C distinct, the claim is that these two statements are equivalent. B is between A and C, and this statement: there exists a number t between 0 and 1 such that the point B can be written this way using a vector description. Here's proof part 1. You'll write proof part 2 in a homework exercise. So proof part 1 is to show that 1 implies 2. If 1 is true, then 2 is true. So notice the structure. We're going to start by assuming that 1 is true. We assume that we've got 3 points ABC that have this betweenness relationship. Now look how this proof is going to end. We need to end by saying that 2 is true. We need to end by saying that that is true. So let's look ahead. We say at the very end, we've shown that B must be of that form. So that has shown that 2 is true. So we have no choice about that structure. Now what? Well, the standard issues that we often have when writing proofs. If you have something that shows up that you know is true that is a defined term, you have no choice about what to do next. You have to unpack that. One thing that this tells us is that ABC must be distinct collinear points. That's part of the definition of betweenness. Now, that's not the only part of the definition of betweenness, but we'll come back to that, the other part later. Now, since those points are distinct and collinear, we know that they all lie on line AC. And we know that in the Euclidean plane, that line can be described using vectors this way. And in that vector description, point A corresponds to this expression when t is equal to 0. And point C corresponds to this expression when that parameter t is equal to the number 1. Now, the function from the line AC to the real numbers, defined in vectors this way, is a ruler for the line. That's using an earlier proposition. From section 3.1, we discussed that when you have a line described in vector form in the Euclidean plane, this function described in vector form is a ruler for that line. And furthermore, by some discussion we had at the end of the video for 3.1, which was also the subject of your exercise 3.1.5, we know that this ruler is what's called a special ruler, has A as origin and C positive. Indeed, we can check that out. Since point A corresponds to t equals 0, and since point C corresponds to t equals 1, when we compute their coordinates, we'll find out that the coordinate of A is, well, we put in that number 0 into that expression, and we get 0 as the coordinate of A. When we compute the coordinate of C, well, we use that number 1 for the value of t, and we build this expression, and we get this as a result. Well, that's a positive number. So let's recap what we've done so far. We suppose that A, B, C were points in the plane with this betweenness relationship. And we use that to be able to say that those must be distinct collinear points. We came up with a description of the line, a vector description of the line that they all lie on, and we came up with a vector description of a ruler, the special ruler for that line. This function is a special ruler. Now, statement 5 is very important. It says that f of b is between f of a and f of c. Those are real numbers. So this symbol is spoken. F of b is between f of a and f of c. Now, why is that true? Well, let's look at my justification. Here I should have said by statement 1. So let's go back up and look at statement 1. Statement 1 says that a-b-c is true. Now my justification says I'm going to use that fact, and I'm going to use theorem 3.2.3, I arrow double I. Well, let's go back up and look at theorem 3.2.3. Here's theorem 3.2.3. This theorem says that these two statements are equivalent. If you know that one of them is true, then you're allowed to claim that the other one is true as well. Well, in our situation, we knew that some points had a certain betweenness relationship. So we knew that I was true. So this theorem tells us that therefore double I must also be true. So let's go back down and look again at how this was used and how it was cited in the proof. In statement 1 of our proof, we knew that these points had this betweenness relationship. So in statement 5, we are allowed to say that the coordinates of those points, the real number coordinates, have this betweenness relationship. And we cite that theorem by writing this. We not only say by theorem 3.2.3, we also say which direction we used that theorem. That theorem doesn't tell us that either of the statements is true. It says if you know one is true, then you're allowed to say the other one is true. So you have to say, when you cite this theorem, which is the one that you knew was true? Well, we knew that I was true. We used the theorem to be able to say that double I was true. And so, therefore, we can say that either this inequality is true, or this should have a less than sign here, or that inequality is true. That's by the previous statement 5 and the definition of betweenness for real numbers. Now, we can be more specific, though. Just knowing that this betweenness relationship is true tells us that either this is true or this is true. But in fact, we know it's got to be this one. The reason is, in statement 4, we figured out that f of a is 0 and f of c was positive. So if f of a is 0 and f of c is positive, we know that f of a is less than f of c. That only happens in that inequality. So of these two possible inequalities that might be true, we know it's got to be this one. Now furthermore, we know that this inequality has to be the one that's true, but also we know that f of a is a number 0, so we can put that there. And we know that f of c is the number, the norm of c minus a, so that can go there. So since f of b has to be between those numbers, then we can write this inequality. But look, f of b is a number that we get by doing this. We know that f of b is obtained by doing this calculation. And so that means since this inequality has got to be true, the value of that parameter has to be a number between 0 and 1. Well, since that number t is a number between 0 and 1, that must mean that the point b must be a point of this form with the number t in that expression being a number between 0 and 1. So all of that is a ton of work, and we end up with the thing that we needed to end up with, that b is a point of this form. So that's the end of proof part 1. In proof part 1, we show that if 1 is true, then 2 is true. And as I said, you'll do proof part 2 in a homework exercise. This is a hard proof. And the proof part 1 that I provided is difficult. It's difficult to follow even a provided proof. So your job is to really digest this proof that I've provided and see if you can kind of run it backwards. Proof part 2 is going to be, suppose that double I is true and prove therefore that I is true. So your job in the homework is going to be proof part 2. Show that if double I is true, then I is true. Let's go on. Now, remark again on how the equivalence theorem gets used in the proof. Remember what I said before, theorem 3.2.3 does not state that either I or double I is true. Theorem 3.2.3 says that these two statements are equivalent. You can only use that theorem in situations where you already know that one of the statements is true. In that situation, that theorem allows you to say that the other statement is true. So when you use an equivalence theorem in a proof, you should be very clear about which statement is already known to be true and which statement the theorem allows us to say is also true. So go back again and look at the way I wrote the justification for statement 5. That justification says very clearly how I use that theorem. We already knew that statement I was true. We're going to use the theorem to allow us to say that statement double I is also true. We knew that statement I was true from statement 1 of the proof. Let's go on. Now I want to talk about a theorem that tells us about existence of points with certain betweenness relationships. Theorem 3.2.6 says, given distinct points A and B in a metric geometry, there exists a point C with B between A and C, and there exists a point D with D between A and B. Now, here is a proof. I'm not going to explain this proof. It's very detailed, and notice that this proof does not have illustrations or justifications. In your homework exercise, you are going to be called upon to justify and illustrate the statements of this proof where indicated. So you're going to end up having to produce 4 justifications and 5 illustrations where indicated. And in your homework exercise, I want you to actually copy down these statements and add to them the justifications and the illustrations. So the end result is that you will have a fleshed out version of this proof. It'll take up a lot more space because of the justifications and the illustrations. Now I want to talk about betweenness of 4 points in a metric geometry. This symbol, A-B-C-D, means that these 4 betweenness relationships are all true. B is between A and C, B is between A and D, C is between A and D, and C is between B and D. We can illustrate that in the following way. So I can draw a bunch of points on the line. Now, what should I add to my illustration to make it clear what I'm referring to? Well, let's put a title. This is a picture of A-B-C-D. But what else? We should draw attention to the fact that all 4 of those relationships are true. So let's do that in the following way. I don't know if that helped or if that made it worse, but the idea is that this symbol means all this stuff. All 4 of these betweenness relationships are true, and they're all illustrated as shown in that diagram. So this is an example of my general approach of always trying to illustrate statements made in geometry. Sometimes the illustrations are more successful than in other times. This is an illustration that, I don't know if it helps or not, but it's good to always try to illustrate and try different ways of illustrating. Let's go on. Now there's a fact about betweenness involving 4 points. Here's the fact. If B is between A and C is between B and D, then B is between A and D and C is between A and D. So in other words, of those 4 betweenness relationships on the previous page, if I know that these first 2 are true, then the last 2 are going to be automatically true, and so then we're allowed to say that big string. Keeping with my general approach, we should try to illustrate this. So this is an if-then statement. So we should have a picture of the hypothesis, and we should have a picture of the conclusion. So let's draw the picture of the hypothesis over here on the left, and draw a picture of the conclusion over here over on the right. Now I'm going to start by drawing a picture of the hypothesis. And I'm going to recycle that picture over on the right. And what this theorem is telling us is that if the stuff on the left is true, then the stuff on the right is true. So I'm going to convey that by putting an arrow. But I want to do a little bit more. I want to try to convey what the statement actually says. The statement says, if these 2 things are true. Well, let's illustrate those on this left diagram. A-B-C, I could illustrate this way. And B-C-D, I could maybe illustrate this way. That illustration shows the configuration of points, but also shows what you're supposed to be noticing about them. You're supposed to be noticing that B is between A and C, and that C is between B and D. Now, what should we illustrate over here on the right diagram? We should illustrate these things. So look, this illustration was the same sort of illustration done on the previous page. The previous page, it was kind of a mess. Maybe it wasn't really helpful. But here it's actually kind of cool. It shows you what you should be paying attention to on the left diagram. Pay attention to that and to that. And what you should be paying attention to on the right diagram. Pay attention to that and to that. This theorem says, or this fact says, that if these 2 green things are true, then these 2 red things are true. Now, how would a proof of this go? Well, think about the proof structure. We have to start by saying, suppose that the given stuff is true, or suppose that the hypothesis is true. And we have to end by saying that that stuff is true. So here's the proof. We have to suppose that the hypothesis is true. Now, this is actually a long proof. It's not until the next page that we can say, therefore, that red stuff is true. Now what else? Well, clearly this first statement has some defined terms in it. So we have to start by unpacking the definition of A-B-C and the definition of B-C-D. So that's what happens in statements 2 and 3. Statements 2 and 3 are unpacking that definition. So again, statement 1 was inevitable, and statement 2 was unpacking. Now, what next? We use the fact that A-B-C is true to say that f of A star f of B star f of C is true. How do we justify that? Well, that's one of those cases where we use that theorem. Theorem 3.2.3 doesn't tell us that either one of these statements is true, but it tells us that if we do know that one is true, then we're allowed to say the other one's true as well. So we used that theorem. We used statement 1 as being the thing that we know is true, and that theorem tells us that therefore we're allowed to say that this is true. So here's another case where I use the equivalence theorem by citing the thing that we know is true, and then cite the theorem and cite the direction that we use the theorem in order to claim that some other statement is true. Now look, the thing that we just introduced this statement, f of b is between f of a and f of c, that's a defined term. So we have to unpack again. The only thing that you can do with a defined expression that you know is true is to unpack it and write what it really means. Well, this symbol means either this or this. That's by the definition of betweenness. So again, we're unpacking that definition of betweenness for real numbers. And we also know that this is true. Again, we use theorem 3.2.3 again. So look, here we've got an or statement. Anytime you have an or statement in a proof, you know that you can follow it up with a proof by cases. So there's going to be two cases. One is the case where this is the inequality that's true, and the other case is going to be the case when this inequality is true. So we're going to get two cases from this big or statement. Well, I'll let you read the remaining details. This is the kind of thing that's actually better to do in at your own pace, reading printed notes. But I just wanted to point out the structure, the idea that we had to begin with that green statement, we have to end with that red statement. That's a recurring theme in this course. The idea that we had to unpack that defined expression, that's a recurring theme in this course. We had to unpack that defined expression. And then a little bit more structure. Once you arrive at an or statement in a proof, then you are setting yourself up for two cases. Case 1, where the green thing is true. Case 2, where the red thing is true. So again, I'll let you read the details, the further details on your own. But I did want to discuss structure, kind of the recurring ideas about structure that are coming up again and again in this course. And again, I'll remind you how the equivalence theorem 3.2.3 gets used in this proof. In the first part of the proof, we use the equivalence theorem in the I arrow double I direction. We knew that some points had an equivalence relationship, and we used the theorem to be able to say that the real number coordinates had that betweenness relationship. But later in the proof, we use theorem 3.2.3 again, but it's in the other direction, the double I arrow single I direction. That's because, look, on statement 11, we know something about the relationship, the betweenness relationship of the real number coordinates. So we use that fact and this theorem to tell us that, therefore, the points have a certain betweenness relationship. So I'll be harping on this throughout the rest of the course. When you use an equivalence theorem in a proof, you need to provide a very thorough justification like that. Well, that's the end of the proof of that theorem, and that's the end of the video. Thank you.